Hi and welcome to another Yosys HQ interview video. Today I'm very happy to be joined by Aleksy. Hi Aleksy.
Hi Matt.
How are you doing?
I'm doing fine. It's almost
Good.
end of the week. How about you?
Yeah. I'm feeling the need for a Friday as well. So could you just tell us your name and your handle and your preferred pronouns?
Yes, my name is Aleksy and that's because it's complicated. Everybody calls me Drom, and or Wavedrom, depend on a social network. And pronouns would be he, him.
Thanks. Okay, yeah. So I know you best through Wavedrom, the tool. So maybe we could kick off by telling us a little bit about that.
Yes, that's surprisingly simple things kind of get popularity more than complex things. That's a little script I wrote, already like 10 years or more ago, to help me and my colleagues to basically create some PDF microarchitectural specs, different projects we were doing because everybody was tired to draw timing diagrams. And I was learning web and JavaScript and said, okay, why not? It's a good exercise to port my Perl script into JavaScript. And that's how it started. It was Google Code back then, and then it became a GitHub, and so it's moving on. And it's slowly gaining popularity. And I'm glad that it's simple, because if it's complex and I need to support too much code, it would be hard. But because it's pretty simple, it's not much of a burden.
I used it to make the kind of the teaser tweet that we put out on the Yosys HQ channel, and I only use it kind of once every 2 or 3 months, and so I always forget the formatting, but it's easy enough to just kind of work it out on the fly. And if you've not used it before, then it's web hosted. You go to a website and you type in some ASCII text, and then that creates a very nice looking timing diagram. And then you can either download that as an image and insert it into your documentation, or you can send a URL to somebody with all that data in there. So then you can get the vector-based version. And one thing I noticed recently was Olof Kindgren, who we've interviewed before, has started using Wavedrom as part of his automatic documentation builds as part of Read the Docs. And that is really nice. So when you push new documentation that might include a timing diagram change, then it will also update the images. Is that something that you kind of thought was going to happen, or is that kind of nice to see that happening?
Yeah, interestingly, so there are so many ways to do diagrams on now, and some of them web based, and some of them I have, for example, browser plugins that allow you to show, like, automatically render diagrams on your GitHub or GitLab account when it find one. So I also have a Lambda function, which is AWS service, where you send the description and you get a SVG back. That's what Olaf was using for his logo, for example, right? There's PWA app, which is like progressive web app application you can install just from wavedrom.com. There is like cross-platform, installable. Different people use it differently. I use also observable HQ notebook, which allow any arbitrary JavaScript, including Wavedrom in there, which is convenient, and people use it in ASCII Doctor. I lost track how many ways you can use it, which is good, because people adopted it to all flows they want or like. And and absolutely, quick learning or real learning tool is a big thing these days, because attention span is kind of shrinking. if you cannot visually like learn something in no time and start using it in 10 minutes, you will lose interest in 20. So you have very short window of opportunity these days to learn something. And also, so it's very simple. There is not much features. I get requests from time to time to add fancy features, but I try to keep it simple, which is good.
Keep it simple. Keep it light.
Yes.
Yeah. So you're working now with SiFive, right?
Yes, that's my day job.
Can you tell us a bit about that?
Yes, so SiFive probably well known by pioneering this RISC-V movement, and riding that wave for a few years already. And I joined SiFive 2.5 years ago because I was super excited to work on the new technologies and just to work with smart people every day. Keep me floating. That's very exciting.
Keeps you on your toes.
Yes, exactly. It's like
Yeah.
when people talk about some crazy things and you barely understand what they're talking about, you feel comfortable. So we are doing the RISC-V course as a visible tip of the iceberg, and selling them as a licensed course to anybody who want to buy one. Bigger stories. We have a few companies that are like our partner, like our federation companies who do chips, go to different markets, Chinese market, Korean market, and also doing chip design as a service. Open 5, I guess it's called now. Yeah, it's one of the companies that can do chips for you. But we also working hard on RISC-V Foundation as a founding member, and contribute to new specs and updated specs, and in general popularizing RISC-V movement as much as we can, which is nice. I like open source very much.
Are you involved in any of the RISC-V groups, the steering groups, or the extension groups, or anything like that?
Right. So primarily interested in a J extension, which is just in time extension, because I'm JavaScript guy, as they call me. So I would be happy if
You're straddling the between JavaScript and hardware.
a full stack is that's what I call it. And yes, so I'm particularly interested to run V8 or Firefox on RISC-V one day, better than anywhere else. And this way, I think we will get a server, we will get a client on RISC-V, and that's a road to success for RISC-V, is get to modern infrastructure quick. And yes, we are open right now to add anything to ISA that required, or will move the story forward with JIT compilers. J extension is one groups I participate actively. There is also vector extension, where I did few vector machines in the past, and I am very excited to work with best vector people in the industry. Our founder Krista Asanovic, he kind of vector guru. And every time I ask a question and get answer, I have to kind of think about it quite a while, just because it's deep. But yes, vector extensions are coming along, and I'm helping as I can to extent of my knowledge. But it's very exciting.
Yeah, so just maybe taking a step back, because I realize that maybe not everyone is totally familiar with the way RISC-V works, but there's like a kind of core instruction set that any RISC-V processor has to support. And then you have the extensions like a floating point extension or the just-in-time or the vector extension. So, and then if you want to, if you're building a chip and that would be useful, then you can just grab that set, like standardized instruction set, and then your chip's going to do this extra stuff for you. So could you give us like some example of applications of where the just-in-time extension and the vector extension would make sense if you were building a new chip? Like, what would be the applications for those extensions?
Yeah, anything more complex than microcontrollers these days has some sort of SIMD extensions, like x86 has SSE, AVX extensions, and ARM has Neon extensions. It's kind of, it's kind of there. If you run Linux, you want a little bit of acceleration. You want to compute four answers per cycle rather than one answer per cycle. You would go for some sort of SIMD extensions, and because people kind of take it as granted on other architectures. People come and say, "Yeah, you have RISC-V processor; it runs Linux, but where is my vector? Where is my SIMD?" The idea behind SIMD was to accelerate some Photoshop and video applications and some filters and do some DSP kind of on the same machine where you run Linux, which is nice. But so the original SIMD that we all use on machines, which are AVX and SSE, SSE, MMX kind of extensions, are kind of chunk, like I may bollocks this term, but it's like a chunk by chunk extensions. And original ideas that came from Cray and the original vector machines was to make a scalable vector. So when you define the vector length, you are not limited by what hardware can do, and hardware decide how to chunk it, how to process it chunk by chunk, depend how much resources it has at the moment, right? So this idea of scalable vector is older than idea of fixed width vectors like SSE, and even though they're solving almost the same problem, so you can do same computations on SSE on a vector machine, they're solving it a little bit differently. And in a world where you have one implementation of x86 or two from two big giants, and that's it, and you just make it compliant and work, the traditional SSE or SIMD extensions would be fine. But in a world where you have a myriad of RISC-V implementations, come out with subset that fits all the needs, it's kind of hard. So scalable vectors in that sense are a more flexible solution. And, I think it's great fit to RISC-V in general.
So what would be an application for that? Say I'm designing a chip and I'm doing this application, so I want to use the vector extension. What kind of applications is it good for accelerating?
Yeah, for example, if you have any client device, you will probably have some sort of camera or screen, and what you want from it, at least, to get some video conferencing, and you want a blur background or something, right? So you can do filter, but you need to do.
You want to multiply every pixel by some value, so then
exactly. You
this
want
big matrix operation
to do some machine learning, detect edge or detect your contour. That's a DSP processing of some sort. And then when you detect the background, you want to blur it so you can apply filter and something, right? So it's even the minimum. We are not talking about 3D graphics or anything, but the minimum video filtering or edge detection or maybe gesture recognition, right? As how many fingers I have, it will be 5 in Roman, but you have to know context and train the model in order to do simple stuff these days. And in order to have a client device, you need some DSP, and the vector comes here very, very well.
Right. Yeah. So anything to do with images, I suppose, because you're doing like huge parallel,
images,
like the same operations over and over again.
Yeah, images, video, audio, and machine learning and DNNs comes very, very handy these days as well.
Mm-hmm.
I don't know how, but we're gonna run.
Everyone's talking about it. Yeah.
Yeah, models everywhere.
Yeah. Cool. What would you say that you're most excited about in terms of working with RISCV?
I'm kind of do-it-yourself person, so I like going deep to turtles. Visit turtles pretty often and have conversation about what full stack means and how deep you can dive into full stack. And I done a few attempts to do processors in my life, and every time it met a license kind of barrier. I can talk about it now, but in Taiwan in 2001-2, we did ARM kind of rip-off processor. And even though it worked and run Windows CE, we would never go to the open market because TSMC would not allow us to do ARM rip-off, right? So even though you design it and you kind of, you own it, but you don't really own it because of this, license compatibility question. So we need more processors, we need more smart things around us, and not only for cheaper, but also some freedom or sovereignty. And when I start talking to different people in different geographies about RISC-V, India and Russia and in China and Taiwan, and everybody talked about, and even Europe, everybody talked about sovereignty. And RISC-V is kind of sovereignty to me, because let's take a European space programs. There was a Leon core, which was like Spark core. And every time I ask them why you haven't switched to ARM, they say, you know what, we need independence. We don't want that our space program get hostage by some corporate somewhere, right? Which get changing address all the time, right? So we don't want to be, it's a long program, so why we should depend on somebody, right? Same words I hear from basically any region in the world, and RISC-V is such opportunity. Work can be redone. It's not too much work to create a processor. It is a lot of work to create a good processor, but still, you better put work up front rather than depend on somebody forever. That's what
nice
keep me excited.
Yeah. So let's take a quick break to hear about Yosys HQ tools and services.
Yosys HQ, open source EDA tools and related software development.
Okay, we're back. Thank you. So let's talk about some of the other tools that you've been involved with. There's one that is called CIRCT with some vowels removed.
Yes.
Can you tell us a bit about that?
Yes, CIRCT without UI is our attempt to make.
Oh, is that like a gag? It's taken the user interface, the UI, out of CIRCT.
Yes, basically, because it's library. I don't know. It's a strange name, but
No, I like it. I like it. CIRCT without UI. Pretty good.
Yeah. So the project started by Chris Latner, who created LLVM and joined SiFive, a year and a half ago, to solve a scalability problem at SiFive, because creating processors is kind of fun, but when you get at a higher scale cluster, processors, out of order cores. We are doing in vector machines, and then go to bigger systems and SoCs. You will figure out that you need very powerful tools to deal with big designs, right? So whatever we have at the moment is okay for some scale, but will go out of fashion very quickly. So Chris brought this idea that on top of LLVM, he built a framework called MLIR. It's multi-layer intermediate representation framework that allow you to build compilers, but not necessarily x86 or ARM compilers like LLVM, but compilers to do other things. It's used in machine learning. It's used in sophisticated tensor processing and whatever fancy now, but it can be used to build the hardware. And when I say hardware, I mean chip design mostly. And yes, so he brought this idea: how about using LLVM and MLIR to describe and keep it in some form in this system? And CIRCT is a playground, or not playground, but a kind of incubator project inside LLVM group. It's circuit.llvm.org. It's include few dialects. Dialect being some kind of subset or abstraction subset that can be used for the compiler. It's not necessarily compiler by itself. It's a kind of a guts of compiler. It's what LLVM for CLang. It's something that intermediate representations that can be worked on, optimized, transformed, and then eventually spit out some form, very local binary, right? So this CIRCT project is an incubator project, and there are regular meeting where multiple companies and multiple universities join in and discuss what are interesting circuit design dialects and forms and transformations they could use in this framework.
It's going a little bit over my head. Could you tell me what problem it's trying to solve? Help me understand.
Right. So SiFive build the processors, for example, using Chisel language. Or there is MyHDL language similar in Python, and there are few.
So that's like just for anyone who doesn't know. So like the kind of the lower level is like Verilog or VHDL, and then there's this kind of a more recent trend of people writing a secondary language like Chisel or nMigen or one of these other ones that you write in Python or Scala or something else, and then you run it through this set of tools like Chisel, and at the end comes Verilog. But then it's not human readable. Well, not that Verilog is particularly human readable, but it's harder to read than normal. So SiFive does your processor development in Chisel, right?
Right. Yeah. We do everything in Chisel, but after you wrote a Chisel program, you compile it into some form, and you do a lot of transformations. We compile it in what we call FIRRTL, FIRRTL.
Have you cut some vowels out of that as well?
It's not my invention for sure.
Yeah. Okay. All right. So that fits between Chisel and Verilog.
Right. Yeah, and then there is a lot of transformations can be done before you get Verilog, and those transformations may be optimizations, maybe something that reshape a form of Verilog before it gets spit out, and those transformations were done kind of by a tool written at Berkeley, and we still use it. It's called FIRRTL compiler. On Chip Alliance FIRRTL, but we want to go forward, and we want to do more things with with this intermediate representation, and that's what yields this new project, which based on the LLVM and MLIR. And we are playing with.
So CIRCT is an alternative to FIRRTL, is it?
It's kind of alternative to FIRRTL and part of a Chisel, and eventually would be more than that, because it's interface with other languages. We are working with other companies who is interested to bridge a high-level synthesis HLS systems to it, and everybody has own favorite language. We're not gonna recruit everybody to drop their favorite Python or language of a choice in favor of one language fits all. We doing a machinery that takes anything, do anything with it, and then spill out the form that you want. That's what CIRCT project is, and
okay, so it's like a kind of intermediary between the final thing that goes into the ASIC compiling tools and whatever you're describing your hardware with.
Yeah, correct. And eventually, there is no limit how it can go down. For example, Yosys itself uses an intermediate representation between Verilog and netlist. It's synthesizing. It also has intermediate form, and we kind of open to that direction as well. So there's nothing stops us to use CIRCT for Yosys, for example, or Verilator, or anybody who interested in building other tools around.
So one advantage of CIRCT would be kind of allowing more portability in designs. You can take designs in whatever different language and then use them with whatever different tools, like a kind
yes,
of...
right. So the major advantage is that CIRCT built on MLIR and LLVM, which are like industry-proven compiler frameworks, which not only reach on functionality but also kind of proven to work, and a lot of people know how to deal with them, and a lot of creativity going on from PhDs of different universities. So a lot of innovation going on there, and it's well managed by different needs. So we don't want to recreate everything from scratch. Whatever functionality tested by machine learning guys, in tensor computations, can be applied and somehow breached with hardware, right? So I think there is merit on reusing as much as you can of a industry kind of class framework.
Yeah, absolutely. I mean, if you've got a design that is very well tested and has a lot of support around it and a lot of things built on top of it, then you want to reuse it if possible.
Yeah. Also, this new wave of machine learning systems bring up new ideas about new architectures. When you compile your model, I can butcher the terminology, but when you create a model, train the model, sometimes you want to run the same model on software. If you have a powerful CPU and the model is quite small, in some cases you want to run the model generated the same way on GPU, sometimes on FPG, sometimes on mix architecture, where on new architecture or mix of architectures, right? So all this fluidity of our architecture is super important these days. You don't want to recreate a model again in different framework. You just want to, I want to make an ASIC that will, just do what I want. Why not to lower it into Verilog or part of it, right? So it's kind of common framework where modus operandi where the people operate these days.
Cool. Okay, so let's switch topic then. in the early days of computers, they were so big and expensive that you would just have one and people would connect to them like a kind of mainframe client server thing. And then as computers got more powerful and more distributed, everyone did their own work on their own computer. And I know that you've got some ideas about kind of going back to more of the client server model. Can you talk a bit about that?
Yeah, I think we are still in client server kind of mode. I used to joke and bet in my use about what will win. Linux, Windows, Mac OS, KDE, GNOME, and so on. But I realized that we kind of missed the point back then, because the web interface basically won, the browser won. So no matter which OS you're running, you're spending most of the time in the browser, and most of the computation you do, you don't realize it, but it's going on in a server somewhere. It's a browser.
Yeah, whenever I run top on my machine, it's always 4 or 5 processes as Firefox at the top.
Yes, exactly. So if you look at the profile, how much memory you spent in which application, it's probably mostly Chrome. And that's reality. It's not that we we want something else. We want convenience. We want something that just work, right? We want reactive, responsive. Like I said with Wavedrom, the power is that you don't learn anything. You just click on something, you go somewhere, it just works. You don't want to install anything. Your attention span is short. Just learn this new application Zencaster by just clicking on it and running it. So it's like now I'm running it. Before you have to download, install,
now we're making a podcast,
buy CD, and these days it's kind of everywhere. So instead of discussing KDE or GNOME, I think we are discussing now, how can we bring what we as engineers used to have on a Linux machine on a server somewhere, where you VNC to some Linux machine and run some Synopsys tool somewhere. Instead of it, we discuss how can you bring this to the web, because it's a new normal now. Right. So part of it comes in different forms. It comes in CI form, where just work on your machine is not good enough. You want to push to Git, and there would be some CI checking out your code, running all standard procedure from scratch, and reporting yes, no, based on latest greatest environment it just created from scratch, right? So we kind of want this environment, and it's very different from what chip designers used to do. I'm logging to Linux server through like VNC, and I'm opening a window, and all these tools are kind of in the past, but we still rely on them. So we need to figure out a way to how do we slowly bring that experience to the web, kind of thing.
And you're working on some tools, aren't you?
Right. Yeah. So that's not exactly my day job. It's still one of my many hobby projects I do. But yes, many people for these 10 years asked, okay, you can do waveform timing diagrams. Can you do big ones? And basically, first crazy idea everybody has is just take VCD file and generate wavedrom diagram from it, right? And it wasn't meant for this. It was meant for the other way around. You create a little tiny timing diagram for your document and render it. So it wasn't meant for it, but demand is there. So at some point, a few years ago, I start thinking about what will it take to make actual VCD viewer, for example, which is infinitely scalable. And when I say infinitely, means that you have to be able to look at the particular region of your space-time continuum while simulation is still growing. Like it's like expanding the universe, simulation is still running, but you already can take a look at the some distance in a time. And it's important because we used to run long simulation overnight and then come in the morning just to see that it's broken in the first 20 milliseconds of a simulation.
Yeah.
Which is okay back then, not now, right? So people want click on something and immediately go there and check and get notification that something broken, click there, go to CI, GitHub Action Travis, whatever CI of your choice, and then see what's broken, where, why, and don't install any tools of it. So yeah, I think the good waveform viewer, like a VCD viewer or whatever format you want viewer, based on the web, which can be used inside browser or inside CI, and also be annotated with all the failure information on top of it. And like Google S, it should be infinitely scalable. Right? It should be able to zoom in the problem or zoom out and see whole picture, or scroll while it's still coming from simulation. That would be a key application for the bringing EDA tools to the web.
To the 21st century.
It's a middle. You don't realize it's almost a middle.
Great. Okay. Is there anything else you want to mention?
Yeah. So in this CIRCT project, I do portion that calls CIRCT Fuzzer, which is a generator of random programs, and it's finding a lot of errors just because when you don't think about you cannot think about all possibilities of your FIRRTL or IR constructions. But Fuzzer don't care; it's just generated, right? It just generate random stuff, and we heavily using Yosys for a logic equivalency. So we run the same random program through two compiler frameworks, one Scala based and one LLVM based. In the end, they not only need to behave the same way, so fail, false positives, false negatives, actual finding errors and so on, but also has to produce some logically equivalent result, which I use Yosys logic equivalency very heavily, and happy with the fact that we have such tools. In essence, I run it 24/7. I run it on such amount of tests that in the end, practically impossible to run with the commercial tools because it will cost you a fortune just to do testing. And it can run on CI, which is very powerful too. So we actually the CIRCT nightly build Docker container comes with Yosys in it, so I can run logic equivalences there. So I really
cool.
enjoy open source tools, and Yosys as an example.
Great. Cool. Okay. And how can people get in touch with you on the internet if they want to say hi or get involved in one of your projects?
So I'm on Twitter with the handle Wavedrom. That's one way. I'm on GitHub, name Drom, and most of the other places also available as a Drom. Please send issues, PRs,
pull requests.
Pull requests on any of my projects or projects on Wavedrom organization, and I'll be back to you eventually.
Great. Okay. Well, thanks very much for your time today, Aleksy. Great talking to you, and I'll see you on the next one.
Thank you, Matt.
Bye-bye.
Bye-bye.